This is part 2 of Making a Scientific Graph video. In part 1, we took a look at how to set up and label a graph properly, how to set a proper scale, and how to plot your points and draw a best fit line. In part 2, we will be looking at analyzing that line. So, the first thing we're going to look at, one important thing that we want to draw a lot of times after we have our best fit line, is to determine the slope of the best fit line. So, of course, your definition of slope from math class is rise over run. Now, what does that mean? A couple different ways we can represent that formula. As delta y over delta x, the little triangle is the Greek letter delta, which in math and science is usually used to represent change in. So you can remember the slope formula this way. Or if you write it out, what is the change in y? Well, it's going to be a y2 minus y1. So you might recognize this form of the slope formula. But either way, they require you to use 2 points from your line, and from any 2 points in the line, you can calculate the slope. So the important thing is the 2 points you pick have to be on your best fit line. Now, a lot of times after people have made a best fit curve, remember when you make the best fit line, a lot of your data points are not actually going to be on the best fit line. So these two here are my data points that I actually collected data from, and if I calculated the slope using those 2 points, I am not going to get the slope of my best fit line. Instead, I'm going to get the slope of this line, which as you can see is quite different than that of my best fit line. So the important thing is you need to pick points that are on your best fit line. Another thing that usually helps you come up with a better value is to pick 2 points that are fairly far apart. So you want to pick 1 point somewhere on the line, up on the top side of the line, and then go down near the bottom side and pick some point there. Now, if you're on graph paper, I like to pick points that are really easy to read, maybe that points that are right on the intersection of the grids that are on the graph paper. So that really doesn't matter as long as you are using points on the line itself. So again, an example is maybe I'll decide to use these 2 points. They're pretty far apart. Both of those points are on the line. Now, neither one of those are points. Actually, this one here on the bottom looks like one I might have collected from my data. The top one definitely is not. To show your work, when you're doing this on a graph, you can go ahead and emphasize the 2 points that you are going to use. Write the coordinates in for those 2 points. And then, of course, as always, anytime you're using a formula to calculate something, I'd like to see the formula written first. Now, whether you use this form or the delta y over the delta x, that's fine. And then we're going to plug our values in. And notice again, I use the term values. This 2.50 is not just 2.50. The unit on it is liters. So I've included the unit in my formula because when we calculate our slope is going to have a unit to it. Okay. Again, in science, as always, we're going to divide the numbers out to get a decimal answer. Do not leave a fraction number as your answer in science. And then again, notice that we do have units. In this case, we get liters per degree Celsius. That is the unit that's on my slope. Now, once we have developed a best fit line and once we have determined the slope, we now have a tool that we can use to make further predictions. So we can answer a question such as this. What is the volume of my balloon going to be at 27 degrees? I never had my balloon at 27 degrees, but we can predict this by looking at this best fit line because the best fit line, we're saying this is the pattern that exists between temperature and volume of my balloon. So we can interpolate that and say, find 27 degrees down here, find the point where it hits the line, come over, and we can make a reading of the volume. And so we can say that my volume, it looks like it's a little bit past the 1.9, so looks like our balloon is going to be about 1.91 liters at that temperature. Okay, that's a prediction. I never had the balloon at 27 degrees Celsius, but using the pattern that we've established, I am making that prediction. We can also do another prediction. Okay, if my balloon was 2.5 liters, well, what temperature is that going to be? Well, again, we just do the same thing. We can interpolate that, and even though I never had my balloon to 2.5 liters, we can predict that when my balloon is at 38 degrees Celsius, it should have a volume of 2.5 liters. Now let's look at another question. Now look at this one. What would the volume of the balloon be when it was at 80 degrees Celsius? Well, there's a slight problem with this one. my highest temperature that I actually had the balloon at was 40 degrees. And since my graph fills the paper, the highest value is 40. And this question is actually off my graph. So there's a couple ways I can answer this. One way is if I'm using a computer, then this is pretty easy. I can just go in and change the scale of my graph. And here's what I did here. I just basically extended my x-axis to 80. And so now we can actually use that new graph and say find 80 degrees there, and we can make a prediction that, well, when I heat it up to 80 degrees, the volume of my balloon is going to be 4.8 liters. Now that would be one way to do it, is to just extend my graph on the computer. Can you think of another way we could have answered that question? Well, you could have done that using your formula for a line. As you probably have done in math class, your y equals mx plus b, you can plug those values in and solve. So you don't always have to extend it from a graph. That would be another way to do this. But the reason why we had to do this for this question is because this question was outside of the interpolating range. The interpolating range, that is the range that I have collected data within. In this case, in this example with our data here, we had the balloon at 10 degrees Celsius, 20 degrees was the lowest temperature we had the balloon at. So we measured it at 20, 25, 30, 35, and 40. 40 was the highest temperature we actually had the balloon at. So anything within this range would be an interpolating question. Okay, but in this case, we were asking 80 degrees. Well, that was way higher than we actually had the balloon at. So that type of a question is outside of the range of tested values. So that is not an interpolating question. That is what's called an extrapolation. And there are some dangers to extrapolating, because what we're doing is we're assuming that this pattern holds true outside of our tested range. Now, it may or may not. We don't know. So you always have to be careful when you're extrapolating, because you have to have that caveat there that we are assuming that the pattern is continuing. Who knows? Maybe at 60 degrees my balloon gets so big that it just pops, or maybe it's reached its maximum size and so it changes at a different rate after it hits a certain size. So you always have to be careful with extrapolating, but you can do it. So take a minute now, pause this video, and just summarize on your paper the difference between interpolating and extrapolating. Okay, now you have drawn a best fit line from our previous video, and so go ahead and look at that best fit line for your Miracle-Gro data, and I want you to go ahead and calculate the slope of your best fit line. Pause the video now and play it when you have an answer. All right, if you have done a good job, we will check your answer now. Now again, this is a best fit line, and if you are doing this graph on a computer, as I did here, when you have the computer draw the best fit line, it will actually give you all kinds of information about that line. In fact, you'll notice when I had it give me the information about my best fit line, it does this y equals mx plus b. And remember, that's your general formula for any straight line. So that's just the generic formula for really any straight line. Now, if we look at the value that it's giving me for slope, in this case, it's giving me a value of 1.02 centimeters per gram. Okay, and now while you might not have exactly the same answer as this, you probably should be within about 0.03, maybe 0.04 of this answer if you did a reasonable job drawing your best fit line and if you correctly calculated your slope. And notice a couple things about the answer. Not only do we want to look to see the number the same, but did you think about sig figs on your answer? If you look at your data chart, I think most of our data in this had about 3 sig figs. Remember, the slope is just dividing the height by the mass. And so since most of those height and mass values had 3 sig figs, if we're dividing, we take our answer to slope to sig figs. Also, did you include a unit when you calculated your slope? Notice our unit here should be centimeters per gram. You want to make sure you get in the habit of including those as well. So again, we've got that information, and again, when your computer's doing this, it will just give this for you. It's a very nice feature. Okay, and remember your general y equals mx plus b. Of course, m represents the slope of the line, b represents the y-intercept, which in this case is 11.8. Remember your definition of y-intercept is, a lot of people say, well, it's where the line hits the edge. Well, that works sometimes, but the best definition is it's the value of y when x is 0. Now, if your edge happens to be an x value of 0, that works. So in this case, it is where the line hits the edge, and my value there is about 11.8 centimeters. That is my y-intercept. But you want to be careful with that. For example, take a look at this one. Go ahead and pause the video, write down the y-intercept, and play when you're ready. Okay, there's my y-intercept there. Actually, that green spot's in the wrong one. It should be up higher. My y-intercept's right up here, which is a value of 2. So if you said 2, you're correct on that one. Here's another one for you to try. What is the y-intercept of this graph? Okay, well, that should look familiar. This is the same graph we had up a couple minutes ago. Again, when x is 0, in this case, my y is 11.8 centimeters. Here's another one for you to try. Pause video again. Come up with your answer. Now, a lot of times when I ask people this question, they tell me that the y-intercept is about 40. Well, that is not the correct answer on this case. And the reason is, in this case, the edge of my graph does not have an x value of 0. Remember, the definition of y-intercept is the value of y when x is 0. So the y-intercept is actually not shown on this graph. So we would either have to use our formula, pop in some values into our y equals mx plus b formula, or we would have to extend the graph, such as what I've done here. And we'll see actually in this case the y-intercept is pretty much 0 on this example. So you want to be careful with that. That's your definition of y-intercept. Also, when we think about an equation, the generic equation for any straight line is y equals mx plus b. Well, in science, we know what y and x are. So if I was writing my equation for this line, I wouldn't say y equals mx plus b. I would actually put in my variables for what each of these guys are. So on this graph, my y-intercept is the height of my plant. So instead of saying y equals, we're going to say height equals. Now, m stands for the slope. We've calculated that. We know what that is. That's 1.02 centimeters per gram. Notice I'm include the units in along with that. Okay, and that point is for any slope of that particular line that we've drawn. And then instead of x, well, my x-axis is the mass of the Miracle-Gro. So we're going to say the height equals 1.02 centimeters per gram times the mass plus, and again, we've established what the y-intercept is. We have a value for that, so it's 11.8. So if I said, well, what is the equation for this line that we've drawn? This is a good specific equation that we can say for that line. So here's another example I want you to try. You made it multiple choice. So you shouldn't need to do much with a calculator on this, but go ahead and pause the video and choose the correct answer, and we'll see if you get it right. Okay, so the correct answer for this one is D. My y, think y equals mx plus b. Well, my y on this graph is the volume. The x on this graph is mass. If you calculate slope, you get an answer of 2. For every 2 up I go 1 over, so that's a value of 2. And the y-intercept in this case is 6. So that's the correct answer for this one. Again, notice we have all that information. Here's another one for you to try. Write a specific equation for this line, and pause the video and play again to check your answer. Okay, if you have the what I have up top here, speed equals negative 5, and MPS stands for meters per second, over meters times the height plus 25, then you did a great job. Again, we're plugging our values. I know what my y value is. It's the speed. Okay, so y equals mx plus b. There's my slope. You have to calculate the slope from what you have here. You've got enough information there, so you come up with a negative 5. Again, don't forget units on slope. It's your y over your x, so it's my MPS over my meters. And then my y-intercept in this case is 25, and really I should have a unit on that 25. I should have MPS on that 25. I was running out of room. So that's how you correctly can write an equation for any linear relationship that you have. So don't forget those skills when you are using those things in class. Okay, very good. We'll see you in class.